Good morning, I'm Zach Dare, and my background is in computer science. I just finished my final year of a bachelor's in software development degree in MTU, and I'll be going on to do my first year of a PhD in September. So I'll be presenting the classification of emotive expression using verbal and nonverbal components of speech. This paper was written with Ryan Donovan and Roy O'Reilly. So the classification of emotive expression from speech fits into the domain of affective computing. Affective computing is the development of technological and informational systems that can accurately detect, categorize, and mimic human emotion. One of the core motivations of affective computing is to provide machines with a level of emotional intelligence, as machines capable of accurately detecting and understanding human emotion provide a number of benefits. These can be such as improving the fluidity in human-to-computer interaction or enabling greater levels of personalization. This can be done in the form of sophisticated responses triggered by specific emotional cues, and these are just two of the many possible benefits. So globally, devices such as Alexa, Siri, Google Assistants are all being used and are pushing the boundaries of human-to-computer interaction through speech. This is leading to a huge growth in the industry. However, a major limitation of these systems is the lack of emotive intelligence, thus leading to one of the main challenges in affective computing, which is the accurate detection of emotive expression from speech. The range of emotions detected in this approach follow basic emotion theory by Ekman, which dictates that there is a subset of emotions that are both discrete and reliably signaled through psychological, behavioral, and neurophysiological activity. These emotions are anger, fear, disgust, joy, sadness, and surprise. Such emotions are considered basic due to their deep roots in the brain's subcortical areas, and they can be considered as a subset of possible emotions and act as the foundation for more complex and nuanced ones. So to overcome the challenge of accurate emotion detection from speech, both the verbal and nonverbal components of speech must be accurately classified in an emotional context. This requires analysis of the verbal components through semantic analysis. One of the issues with the verbal content is the potential lack of emotive words, or another being the presence of sarcasm or colloquialisms or other complex verbal aspects. Similarly, the nonverbal components of speech require modeling to outline the relationship between the acoustic features and emotive expression. This is typically found in the form of affective prosody, which is the acoustic features such as tone, pitch, energy, etc. So for the components of speech, the information and emotive expression, which is transferred through speech, can be isolated into two distinct modalities. The first being the nonverbal components, known as affective prosody, which again are the acoustic features belonging to an audio signal. These contain the subtle aspects of speech and provide further insights into the emotion exhibited on a subtle level. The second modality is known as the verbal components, which is comprised of the spoken words, specifically words with emotive associations, in order to provide insights into the actual meaning behind the speech. This is analyzed through semantic analysis, which is the process of relating syntactic structures from sentences. When solely analyzing each modality individually, the emotive expression can potentially be misclassified. For example, in affective prosody analysis, an actor can imitate anger by speaking loudly or with authority, despite the spoken content actually being neutral. Similarly, for the verbal modality, a sentence may contain words that in isolation are negative, but in the context of the sentence are not. Or the sentence may contain no emotive words at all, being completely neutral and potentially leading to a misclassification. This highlights the benefits and essentially the requirement of a bimodal analysis for emotive expression in speech. So the research question that's investigated is to identify the strengths and limitations of a generalized bimodal approach for emotive expression analysis. The research objectives then are to assess whether a generic machine learning approach can offer improved results in emotive expression classification, also to identify the strengths and limitations of a bimodal-based emotion classification in relation to the generalizability across datasets, and also to establish a baseline model for bimodal-based emotion classification to enable comparisons with future state-of-the-art machine learning approaches. So our approach, two emotive audio datasets are used, which are the Ryerson Audiovisual Database of Emotional Speech and Song, or RAVDES, and the Surrey Audiovisual Expressed Emotion Dataset, also SEV. And one emotive text dataset was also used, the International Survey on Emotion Antecedents and Reactions, or ICER. The strength of the RAVDES dataset is that it incorporates a large number of utterances and an equal amount of male and female actors. However, the weakness of the RAVDES dataset is it consists of solely two neutral statements both neutral from a semantic perspective. The strength of the SAV dataset is that it incorporates emotion-specific sentences, which avoids the issue of performing semantic analysis on text that's neutral. One of the main weaknesses of SAV is that it includes only male actors, which may impair the generalizability of any models trained on this dataset. And finally then, the strength of the ICER dataset is that it provides a large corpus of text per basic emotion to enable the training of semantic analysis-based models. And one notable weakness of the ICER dataset for the purposes of this paper is that it utilizes only a subset of the basic emotions, with the emotion surprise absent. So to meet our research objectives, here is the proposed approach, which is a workflow that utilizes two machine learning models and consists of two unimodal channels for conducting affective prosody and semantic analysis that operate in parallel and thereafter combined to enable a bimodal analysis for each emotion classification. So in terms of the prosody channel, the audio data is sampled from two audio datasets. The relevant features are extracted and utilized for the training of a nonverbal model for emotive classification. Then in terms of the semantic channel, lexical data is sampled from the two audio and one text dataset, and the relevant features are extracted and then utilized in the training of the verbal model. These unimodality models are then combined into an ensemble in the form of a meta-model, resulting in the desired bimodal analysis. So the following are the components of speech in their technical feature form. So firstly is a visualization of the emotive audio sample, and the relevant nonverbal components were extracted using the Python library, the Python audio analysis library known as Librosa. So these relevant features are the Mel-frequency Cepstral Coefficients, which represent the overall shape of a signal spectrum, the zero crossing rate, which is the rate of change from positive to negative or negative to positive in an audio signal, and also the Chroma Energy Normalised, which is a statistic extracted from a subset of frames to generate normalized values quantifying the deviations in tempo or articulation or pitch or more. As for the verbal features, the spoken words are converted into one of two feature vectors using vectorization, resulting in vectorized labeled emotional sentences, VLES, where common stop words were not removed, and processed vectorized labeled emotional sentences, PVLES, where stop words were removed, both of which can be considered to be bag of words models. Additionally, a transcription experiment was conducted using the Google Transcription API to extract the verbal components from the audio. However, this wasn't included in the paper as the verbal content was actually provided in the audio datasets in the form of key letters that could be used to extract the metadata from the file names. So then, our nonverbal model is a CNN that was first trained on the expanded set of nonverbal features extracted from the audio datasets. This training procedure used 5-fold cross-validation, took place over 300 epochs, and uses a batch size of 16. During training at each epoch, the model is evaluated using a test set of previously unseen data, and this provides accurate reflection of the model's performance. The verbal model is a logistic regression classifier. Logistic regression was chosen as, in comparison to similar models such as support vector machines or random forest, it performs more efficiently due to faster training speed on a large feature vector. So given the classes of emotion, the implemented classifier could be considered as a one versus rest LR model, and one versus rest is a is a method that enables multi-class classifications to be conducted on binary classification models, and this is accomplished by splitting the multi-class problem into a series of binary classifications. So to enable emotion classifications on bimodal data, an ensemble was constructed in the form of a meta-model, which is again a logistic regression classifier. The feature vector used for this meta-model is a concatenation of the returned weights for each emotion from the nonverbal CNN and the emotional classification returned from the verbal LR model for each prediction. The purpose of this is to leverage the performance and to compensate for any misclassifications of each of these single modality models. So onto the classification results. Firstly, we have the nonverbal classification results that show that our approach is outperformed by a state-of-the-art approach on the RABDIS dataset. However, for the SAV dataset, it greatly outperforms the state-of-the-art research. Then secondly, we can see that in the verbal classification results, the accuracy on the RABDIS is extremely low. However, this is to be expected due to the lack of emotive verbal components in the audio samples. In contrast, the verbal model classifies emotion in the CV dataset to a high degree of accuracy due to a greater variation in emotional sentences. In a comparison against a state-of-the-art approach, the ICER dataset was used, which showed the verbal model being outperformed. This can be attributed to a different and potentially smaller subset of emotions that were analyzed by the external approach. And then finally, the bimodal approach can be seen performing very closely to the state-of-the-art approach on the RAVDIS dataset, despite the data still consisting of the two neutral semantic statements, reducing the overall accuracy. And then, however, the results showed that when fruitful analysis can be conducted on each modality, this combined bimodal approach will outperform the individual modalities, and that's as seen in CV, which also outperformed the state-of-the-art bimodal approach. So then to conclude, the discrepancy in the bimodal model's performance relative to the unimodality models between these datasets highlights the strengths and weaknesses of a bimodal approach. So in terms of strengths, when the datasets utilized include sufficient emotive content to enable fruitful emotive analysis, as seen in the CV dataset, then this hybrid approach outperforms those unimodal approaches. This finding stresses the importance of curating datasets containing sufficient emotive content in each modality in order to provide accurate emotion classification of speech. This furthers the goals of affective computing by enabling the potential future application of an accurate emotion detection in machines. So, as part of future work, enhancements will be made to accommodate for the audible variances stemming from differences in language, gender, age, and many more external factors in order to increase the generalizability and the usability. And that's everything. So thank you very much, and now I'll answer any questions.